morning, friends. Indeed, I am very happy as I am coming to the end of this course, and today is my second last chapter or the lecture for this course, Aircraft Stability and Control. I am in the question and answer session of the question bank, and today I am taking the question bank of module 4, which is perturbed equation of motion and its derivatives. As you know that we have covered most of the chapters previously, starting from module 1, that is longitudinal static stability. Then we have started with module 2, which is lateral and directional static stability. Module 3 was aircraft equations of motion. Then module 4 was perturbed equations of motions, and in that we have gone through the different derivatives we have already studied. Then last but not the least was dynamic stability, and in dynamic stability we have seen different modes of the aircraft. Then there's damping, natural frequency, damped frequency, time of response, also mode, that is forward mode, longitudinal mode, lateral mode, spiral modes. These all things we have already covered. Today I am discussing about question and answer of module 4, which is perturbed equation of motion. In today's class I am going to discuss following topic, and in this topic I will take some questions and these questions will be answered. So in this, first one is Mach-Tuck derivative, then the second one is U by U1 derivative, third one is roll rate derivatives, then effect of roll rate on aircraft stability, then roll helix angle and cross derivatives. So these points I will be discussing with some examples and some figures. First I am going to discuss about Mach-Tuck derivative. And what is the Mach-Tuck derivative? So the derivative CMU result from changes in CM0 and the aerodynamic center location with changes with forward speed. Probably the most notable effect on CMU is the aft shift in aerodynamic center that occurs in the subsonic transonic speed range. As the aerodynamic center moves aft, a negative pitching moment results that typically results in a negative CMU. Thus, in this range, the aircraft tends to experience a nose-down pitching moment with increasing speed. This phenomena is commonly referred to as a Mach-Tuck, as a characteristic that caused the crash of several high-speed subsonic aircraft that were not able to pull out of the steep dive as the speed increased and CMU becomes more negative. As a result, CMU is commonly called the Mach-Tuck derivative. Here CM1 is the steady state aerodynamic pitching moment. It will be non-zero for cases where a thrust pitching moment must be counteracted by an aerodynamic pitching moment to trim the aircraft to a total pitch moment of 0. For all other cases, such as gliders and power of flight, CMU will be 0. Okay, so here we can see what is the Mach-Tuck derivative. It is a natural phenomenon. Once the aircraft is flying at the subsonic speed, most of the time the aerodynamic center of this aircraft will be at C by 4, quarter chord length of the wing chord. at c by 4. But as the aircraft is speeding and it is reaching towards the near the Mach or above the critical Mach number, the shock wave start forming, and these shock wave will start, and this the aerodynamic center will start moving backward. Center of gravity is there, but if initially the AC is here, but as the speed is increasing near the or about the subsonics to critical Mach number, and if it is reaching near the sonic speed, the aerodynamic center start going backward. So what will happen if CG is here and initially it was here, it will be little, but as the aerodynamic center moves backward, that is happening during supersonic flight, and it will nose down. So the Cm here, if you see here, dCm by du is be much or high negative. If like this, then what will happen if this is the initially, this is the CG, initially it was here AC and M is here 0.4. As you increase M 0.8, this AC may be here. This is AC 1. So the lift will act here, and this distance has increased. So aircraft will, Cm will be down. So minus Cm or nose down tendency will be experienced. This nose down tendency during high speed of the aircraft is called the Mach tuck. It will try to nose down. Aircraft, it is moving like this as the speed is increased to near Mach number due to shifting of the, it is moving like this. For a low subsonic case, the aerodynamic center will be nearly c by 4. But as the speed is increased, this c by 4 may be c by 3, c by 2. So it is going backward. As it is going backward, the force which is acting behind, a lever will act and it will try to make nose down. And if this nose down is so heavily in high speed aircraft, it is nose down it is making, aircrafts are not able to recover. So this is making a very huge problem for the aircraft to recover, and number of accidents have happened in past. So we should understand that what is the Mach tuck derivative and how we can eliminate and how much is permitted. So as a designer, as an engineer, for any high speed aircraft, we must be very much careful about that, about the Mach tuck derivative, that is called the CMU, and CMU is a dCm by du. So it is CM1 minus CM2 divided by U1 minus U2. So CMU is commonly called the Mach tuck derivative, and this phenomena due to the shifting of aerodynamic center and this tendency of the nose to going down, this is called the Mach tuck. This phenomena we have to understood very carefully. Now here in this diagram, you can see here that this is the wing, and you know that in the supersonic airflow, a very high lift will be generated in this zone. In this side, from here to here, this is a high lift zone. High lift zone. But here, due to this shock wave, here it becomes subsonic and lift is tremendously reduced. Lift is reduced. So what happened? Initially, it was acting here. The AC is here, but in high speed, AC will be shifting here backward. So lift will act here. And if the CG is here, it will try to nose down. Okay. So Mach tuck is an aerodynamic effect whereby the nose of an aircraft tends to pitch down as the airflow around the wing reaches supersonic speed. This dividing tendency is also known as a tuck under. This other name is of this tendency is called tuck under. the aircraft will experience this effect significantly below Mach 1. So, critical Mach number 0.7 to 0.95, you will experience this problem. And it's very high, this if it is M2 and all, this will be further avoided. Now, next derivative is U by U1 derivative, and is, so we have to find out dou FAZ by dou U by U1. This is called the U by U1 derivative. So we know that FAZ, F means force, aerodynamic force in z direction, means towards the lift. So it is a CZ Q into S, where Q bar is a dynamic pressure, C is a constant, S is the area of the wing. Using the same approach as this, we have that dFAZ by du by u1. So here CZ QS divided by dou u by u1, and this is at steady state case. So here we can write dCZ by du by u1 QS plus CZ as dou Q by dou u by u1. Okay, so we can see from the figure 6.4 that this CZ is equal to what? Minus CL cos alpha minus CD sin alpha. Okay, so this minus CL cos alpha minus CD, it is a CZ. So now, with assumption of small perturbation, this becomes, because we are here taking the assumption of small perturbation. So now this CZ is assumed to be proportionally equal to the minus CL. We have neglected the angles, minus CL minus CD into alpha. So now dou CZ by dou U by U1 is approximated equal to minus dCL by du by U1 minus dCL by du by U1 into alpha at steady state condition. From equation this one, 6.24, at the steady state condition, this alpha is equal to 0. So if we put this alpha here is equal to 0, this term will be 0. Okay, so here dCZ by du by u1 approximated is equal to minus dou CL by dou u by u1, or we can write here minus CLU. So here this is CLU represents the change in lift coefficient with respect to the velocity. As we increase the velocity, how much change in coefficient of lift increases. The dou Q bar by dou U by U1 derivative in equation 6.23 follows the same development as found in this equation. Dou Q bar by dou U by U1 is equal to 2Q1. Incorporating in this 2, we are going to get the CZ is equal to CL1 at steady state condition. So here we can write that dou FAZ by dou U by U1 is equal to minus CLU plus 2CL1 Q1. Yes. So here we can see that here this derivative dou CZ by dou U by U1 is equal to minus CLU. So it means at U 50 meter per second, it is U1, CL1 is 0.6. At U2, 100 meter per second, CL2 is 0.8. So dCL by du is equal to 0.8 minus 0.6 divided by 100 minus 50. So you will get here 0.2 divided by 50. So 0.004. Okay, so this is the, and this actually it is will be in the negative direction. Okay, so in this way we can find out this derivative. The derivative CMU results from change in okay. So now next derivative is what is roll rate? That is PB by 2U1 derivatives. So here dou LA by dou PB by 2U1 is equal to dou CL by dou PB by 2U1 Q1 SB is equal to CLP Q1 SB. The derivative CLP is called the roll damping derivative. The derivative CLP here, this is called the roll damping derivative. So roll damping, what is the meaning of roll derivative? Damping. So just you see here, aircraft is flying like this. You have given a roll like this. So one force will act to oppose this, like this. And it is happening due to two things. If you roll like this, initially the lift vector is like this, it is flying. As you roll, lift vector is tilted. So one force will act, one component of this lift will act in this direction. It will try to drift like this. So beta will be generated. A side slip will be generated. This side slip will act on this vertical fin and this will try to make. This is called damping. It is called roll damping. So this thing we have to understand, and it is called PB by 2U1 derivative. So here delta LA by delta PB by 2U1 is equal to delta CL by delta PB by 2U1, and L we have written CL Q1 SB. So this delta CL by PB by 2U1, this is called CLP and Q1 SB, where Q1 is a steady state dynamic pressure. So here this CLP, the derivative CLP is called the roll damping derivative. It represents the change in rolling moment coefficient with respect to non-dimensional roll rate and is usually negative, providing a moment that opposes the direction of the roll rate. CLP is a very important factor for lateral directional dynamic stability characteristics. Three aircraft's components have a primary influence on the value of CLP, that is the wing, the vertical tail, the horizontal tail and the vertical tail. So just I am going to describe how this CLP and these three components are working on this CLP or roll damping derivative. First I will take the wing. Suppose this wing is upside or the downside as per the wing location. If it is a higher winger, it will give more stability because the CLP, the roll damping derivative, will be high in the high wing configuration. But if you take this same wing to the lower wing, then it will not be, more roll damping derivative will not be generated. To have the lower wing to generate the roll damping, we should have the dihedral. We have to, dihedral means this wing is made a little upward like this. Like this. So it is called the dihedral. If you make both the wing dihedral, some angle gamma, then this will generate a roll damping derivative. Third case I have just now explained. Again I am telling that how this vertical tail is very, very important and horizontal tail is also very important, because as it is rolling down, this tail is also going down and this will generate a upward force and it will try to make. Wing also make, the tail also make. But how this vertical fin is making aircraft roll stable or the lateral and directional static stable. Just aircraft is flying like this with this much lift. You have rolled this aircraft. The net vector of this lift is also turned and there is likely to be a force. One component of the force, the horizontal, will act in this direction. So it is going like this, it will drift like this. So there will be a side angle will be generated here, and this side angle beta will give the hit here and a Y force will be acted in this direction, negative direction. This is the positive Y and this is the negative. So this way, and aerodynamic center is much ahead than the fuselage reference line. So this force Cy into this distance, vertical distance from here to here, this will try to make again damp. So these three components are playing very important role to obtain the roll rate damping derivatives. Now it is, what is the effect of roll rate? So this we can see here. Here we have the diagram, and here the PB by 2 is mentioned here. Roll rate induced a vertical velocity contribution on wing and horizontal tail. At wing tip, due to roll rate, it has a vertical velocity PB by 2. This component decreases as per distance from the fuselage. Just you can see here in this diagram. So here is the right tip and here is the left tip. So if right wing is going down, then what will happen? This is the span B. So if it is down, going down like this, you have given a plus P. You have given a plus P. Then what will happen? This PB by 2 and this PB by 2. So a net PB by 2 will act, and you can see that it will try to rotate this aircraft opposite to this. So it is giving, and here if you see the velocity distribution of the vertical velocity, at the center it will be 0, and at you go at the tip, a huge amount of force will act in this, the tip. So, and this both are in the same direction. You just see it is like this, both are making the rolling moment in the same direction. This is also trying to make clockwise, and this is also trying to make the plus, and this is also on to plus. But what is this? It is opposing this. Okay. So in this way, this roll rate will affect the, and it will give the damping on the aircraft rolling moment. What is the effect of wing tip angle of attack due to roll rate? So we have seen that roll rate PB by 2U1, and how this angle of attack on the different positions will make the aircraft in roll rate, and what is the effect of tip angle of attack. We can see here that this vertical velocity due to roll rate changes the aircraft angle of attack at the left and the right wing tip. For a positive roll rate means right wing going down. An increase in angle of attack is experienced on the right wing. Okay? And a decrease in the angle of attack in the experience on the left wing. An increase in lift on the right wing and decrease in lift on the this left wing. Just you can see here, this is the left wing and this is the right wing. This is the right and this is the left. So what will happen here? You see here, this is the horizontal velocity, and here also this U1 here, U1 here, both are common. This is equal to this. But what will happen? It is upward. PB by 2, this is upward and this is the downward. So here this angle of attack is minus. In left wing, you will experience a minus angle of attack, and in this you will have experience a plus angle of attack. So here lift will be in this direction and here will be in this direction. So this is the advantage, and this roll rate will try to make the right wing which is going down, it will give additional angle of attack. So it will again reverse back. So this is the objective of this problem. Now, a positive roll rate creates a force on the tail in the negative y direction. Just now, this, if it is a positive roll rate, just you can see here. So if it is positive roll rate, a negative yaw force, a negative y direction force, here a negative y in this direction force will act. So just you can see here, if this is rolling like this, I told you initially it is like this, it is flying, but as you roll like this, a component will be generating in this direction. This is called the side component, and this side component will try to drift towards the right. Due to this, a side slip angle will be generated, and this side slip angle will act on this. So this vertical fin will generate a force in this direction. It is called negative Y. So this negative Y will try to roll because this aerodynamic center of this vertical tail is above to the fuselage reference line. So it will have a moment and it will try to make in this direction. So a positive roll rate, this is the positive roll rate on the tail, is a negative Y direction force. Just now I have shown. We call this side force Fs, where Fay is equal to minus Fs. So a negative force minus Fs is generated. You can see in this diagram also, if it is rolling like this, a force Fs will generate in this direction. So center of pressure of the tail is here, and this force into this ZV means Fs into ZV, and this direction will be what? In this direction. It will, if this is going down, then a force will act in this and it will make, this is the positive Y and this is the negative Y. So like this, here if you see, this side is a negative Y and this side positive. So if your right wing is down, this will generate like this and this is a minus Y. So in this way, we can see that the vertical tail is playing very important role for this. In this, if you can see this figure here, analyzes the velocity component at the center of the pressure of the aircraft. There is a velocity component in the x direction because of the forward velocity, and a velocity component in the y direction because of the roll rate p. So here we can see that here u1 is the forward velocity, and this v is equal to pzv. This is the like a here also one force. So a net force, a angle of attack will be generated here. This is the delta alpha. So view from top. If you see from the top, a real your flow will experience on the vertical tail in this direction. That makes a side force in the y direction. Now I am going to discuss about roll helix angle. So the absolute value of this change in angle of attack at the wing tip. So we have seen that at the wing tip, there is a change in angle of attack from the right wing to the left wing. This alpha, and this is called PB by 2U1, is called the roll helix angle. So we can see here in this diagram. So if you see here, the angle of here is more plus and this is a minus. So how much change in the plus side and how much change in the minus side? This gives a new angle, and this is going in this line. This. So this angle you can call the roll helix angle. Okay, so the absolute value of this change in angle of attack at the wing tip due to roll rate PB by 2U1 is called the roll helix angle. It provides the basis for the form of the non-dimensional approach used for angular rate. The roll helix angle has a physical meaning as well. It can be thought of as generally as the angle that the wing tip light would make with the horizon for an aircraft undergoing roll rate. Very nice. Just you see that, what is the meaning? All the wings are equipped with right side and the left side with the red or the green light. If aircraft is rolling like this, the red light and this green light, there will be an angle. So this roll helix angle represents a new location of the wing tip. So in night, if you can see how much is angle your aircraft is making during the roll. That is the importance of the roll helix angle in this case. Okay, now next derivative which I am going to discuss is about what is cross derivative. So here we can see that the final PV by 2U1 derivative to be considered is dou NA by dou PB by 2U1. In a similar manner, we have now here dou NA by dou PB by 2U1, where NA is what? It is a yawing moment. PB by 2U1 is equal to, here NA we can write Cn Q bar SB divided by rho dou PB by 2U1. So this dou Cn by dou PB by 2n we can write as a Cnp, and this Cnp is called the cross derivative, and here Q1 SB. This Cnp is called the cross derivative because it represents the change in yawing moment coefficient, a moment about the z-axis because of the non-dimensional roll rate. Means if you roll, yawing will take place. That is the meaning of Cnp, dCn by dP. It means if you roll, yaw will be there. And how much? It is called the cross because both are coupled. The wing and vertical tail are the being rolled away from. So just I am explaining here again. What do you mean by a cross derivative? So assume that your aircraft is moving in this way and you have given a yaw. You have given a yaw. Then what will happen? This, if you are at the right side, you are turning or you are giving your nose towards the right, the left wing will experience more velocity because its radius is outer side, and this, the right wing, will experience a less velocity. This will generate, the left wing will generate the high lift and right wing will generate a low lift. So you are turning to right, but it is rolling also. So that is the meaning here Cnp. So Cnp is called the cross derivative because it represents the change in yawing moment coefficients, that is Cn, about the z-axis because of the non-dimensional change in roll rate. The wing and vertical tail are being rolled away from. So this wing and the vertical tail, they are away from. They are going away. So that is the meaning of the cross derivative. So once we talk about the cross derivative, it indicates that the yawing moment coefficient Cn and our roll rate P, both are coupled each other, and if you make the changes in Cn, the Cp or dP will also change. That we have to ensure. Now I am going to talk about the contribution of the wing in Cnp. So this roll Cnp, if you see, Cnp is what? It is a cross derivative. So this, how the wings are affecting the cross derivative or Cnp. The wing contribute to Cnp in three ways that will be addressed qualitatively. The first contribution comes from the first case, increase in drag that results from the increase in angle of attack on the wing being rolled into. Very nice. So how these things are happening? And decrease on the drag that results from the decrease in angle of attack on the wing being rolled into. So just I am explaining again. Here it is first point, increase in drag that results from the increase in angle of attack. So you see here that if I want aircraft is going like this, you have made like this. In this, angle of attack will increase. In this, angle of attack will decrease. Here, additional lift will be generated. Here, some less lift will be generated. This additional lift will generate the drag in this direction. And here also, drag will be less than this. So aircraft will try to nose yaw towards the right. Okay. And Same way is happening in other wing. If the angle of attack is decreased, the drag will also decrease. So in this way, if you are changing the angle of attack, the drag amount will also change, and this will also make the aircraft to yaw. So we are not making yaw, we are only changing roll, but due to this roll, angle of attack on the left and the right both are different, and they will also produce a different drag, and this drag will pull in the horizontal XY plane. So it will make like this, or it will make like this as per your roll conditions. So that is the contribution of the wing. The increased drag on that results on the right wing and decreased drag that results on the left wing will provide a positive yawing moment to the aircraft, resulting in a positive contribution to CNP. So how? Just positive. So if your aircraft is rolled, the right wing will experience a more lift, more drag. Left will experience a less lift and less drag. This will try to make drag is more, so it will pull like this, and this will go right. So it is a positive CNP. The increase in angle of attack on the right wing results in tilting of the lift vector forward, while the decrease in angle of attack on the left wing provides an off tilting of the lift vector. The net result is a negative contribution to yawing moment, thus a negative contribution to CNP. So a negative contribution of CNP by other. So just you can see about the right wing and the left wing, and this same things are explained here. So about the right wing will give a positive CNP. This will give a negative CNP, and how? Just you can see here. In the right wing, if you see, this is the U1 and this is upward, PB by 2. This angle is increased. This much angle is increased here. Okay. So now initially this was the lift. Now this lift is increased to this much, and this is now L by delta L. So this much lift is increased from initial condition on the right wing. Okay, this is the right wing here. So if you are rolled like this is the right wing, this much going upward. But what happened in the left wing? You see here, this is the U1, a forward velocity, PB by 2. This velocity is going downward. So you have the angle of attack as a minus PB by 2 U1. So here the lift, suppose here L by delta L, here initially it was the L, now this is L minus delta L. And also the direction of this thing is changed. If you see the direction of this and direction of this, the direction is also not the same. This will try to make this aircraft as negative like this. It will counter balance the aircraft roll. Okay, so these aspects we have to understand very well. So now I am just continuation of this. If you see the top view of the aircraft, there is a greater tendency for a positive side force to develop at the right wing tip as the flow migrates from the lower surface to the low pressure upper surface. At the left wing tip, a lower magnitude negative side force develops because the pressure on the left wing upper surface is higher. So here, this you can see that negative yawing moment results here. So here if you see a net positive side force in this direction, and this will make the aircraft to turn like this as so shown in this aircraft. And this force here, it will be less in the left wing. This is the left wing and this is the right wing. So like this will try to move the aircraft in this direction. Next, the net results should be positive side force acting through the right wing tip. This is the right wing and it is a positive side force is acting. If this side force act behind the CG, a negative yawing moment results and the wing tip side force effect make the negative contribution to CNP. So if you can see this is the CG and it is a behind here. So this will act as a negative side force, and if this is here, if this side force acts in front of this CG, which is not possible, normally it is not, a positive yawing moment results and the wing tip side force effects make a positive contribution to the CNP. The wing tip side force effect is most pronounced on low aspect ratio wings, strong wing tip vertices with relative thick wing tip. So if the wing tips are thick, this type of tendency is experienced very well. So these are the today's, and hope this aspect is very much clear for you all, and this will be helping to understand the concept of this. So here we can see that again the net result should be positive, side force acting through the right wing. So here we can see if this side force is positive, y is positive as shown here, and if this resultant working behind the CG here, so the moment will be negative, minus Cm, like this. It is not Cm, Cn, minus Cn. This is a minus Cn. But assume that this is acting somewhere here. This y here. So what will happen? This will try to move in this direction. This force will try to move in this direction and aircraft will be in opposite direction, which is not normally done. So this side force act in front of the CG, which is unusual. A positive yawing moment result and the wing tip side force affect a positive contribution to CNP. The wing tip side force effect is most pronounced on low aspect ratio wing. Okay, so in this note, these are the references: Robert C. Nelson, Aircraft Stability and Control. Also, the Introduction to Flight Mechanics by R. Yachout is also a very good book. In that book, it is very much clearly mentioned these all topics which we all have to understand about that. So, if any query existing, you are welcome to ask me in my email. Okay, so thank you very much for joining the class. Please be tuned for my next classes. I will be very glad to go for my last class, which is very soon it will be available. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.